Okay, last week we discussed the basic principles of learning from data, and we implemented the perceptron. Today we're going to go over the types of data, the types of learning, and then also revisit the perceptron and kind of clean up the code that we wrote last time, okay? So I'll start with kind of like an outline of how we're going to move forward. So I'll begin with what's called supervised learning. Okay, so supervised learning is what we saw last week, where we have some collection of data points. Okay. Say there's n data points that we have. Okay, so where we have features represented by the vectors x1 through xn, and then we have the labels represented by y1 through yn. So in supervised learning, these labels are known. Okay, so there's been a supervisor that has taken the time to go through and look at the data and give them the correct labels. So this is supervised learning. Okay. And supervised learning algorithms will use this data to learn to predict these labels accurately on this data set that you have in order to make predictions about data that you haven't seen yet as to what their labels might be. And the algorithms that we're going to cover that are supervised learning algorithms, well, there's the perceptron. And variations of the perceptron. There's linear regression, which a lot of you have seen before. There's logistic regression. Which maybe some of you have seen before. There's k-nearest neighbors. Okay, and actually, let me check something real fast. Make sure. What am I doing here? And then there are neural nets, or what I'll call deep learning. So these would be the main supervised learning techniques that we're going to use, and for each of these, there's going to be variations of them. So there's like a few different ways to implement the perceptron, a few different ways to implement linear regression, logistic regression. K-nearest neighbors is only like one way, but you can vary it by choosing K. And then deep learning, which is neural nets. Now, within these algorithms, there's two different tasks. There is classification, and then there's prediction. So classification would be like the perceptron, where you're trying to classify these points as a certain label, whereas prediction would be like regression. Oh, I almost forgot one. Decision trees and regression trees. Regression typically will refer to predicting some numerical value. But you can also use regression to make classification in certain scenarios. So for example, logistic regression will be a classifier. Perceptron classification, k-nearest neighbors classification, deep learning classification. Okay. In the special case that you're trying to predict whether or not a object is one of two things, then you have binary classification, which is exactly what the perceptron was. Okay. So this is going to take up the beginning of our semester. So we'll be doing these things up until probably the end of October. In deep learning, it's going to take us probably like about a week and a half just to get through the mathematics behind it before we start implementing it. Okay. So this is supervised learning. Known labels, you use this information to make predictions as to what the label should be for a given a new data point. Okay. Okay, so the next one is unsupervised learning. So here, you have features that have been measured, in this case, in features, but you don't know the labels. And the job of unsupervised learning algorithms is to make predictions as to what the possible labels might be on that data set. So for example, if you have like two features, right? Say like x1 and x2, right? And you just plot data, so 2, you can't see that. Something like this, right? If you don't know the labels ahead of time, how can you cluster this data and kind of form your own labels? So one clustering option might be like maybe those are of the same type and these are of the same type, right? And you don't know, but you make a prediction that they are. Or another way that you could have clustered these data points would be something like maybe there and then there. And we will cover two algorithms, but the main one that we will look at for unsupervised learning is called k-means cluster. Okay, so that's the main algorithm that we're going to look at for unsupervised learning. Okay. Now there are two other types of learning. Online learning, which is kind of like a continuous supervised learning. And then there's reinforcement learning, which is sort of a mix of supervised and unsupervised learning. But we're primarily going to focus on supervised versus unsupervised, or supervised and unsupervised. Okay. Also, we're going to talk about generating artificial data. Like, how do you generate data to run these models on to test whether or not they're working on something that you've generated yourself instead of finding your own data sets. Okay. So with the Perceptron algorithm, we have a binary classifier. You're either one thing or another, right? So let me go ahead and pull up that code from last time. Okay. 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 And please feel free to message me or say something out loud about any of the code if you don't understand it. So again, I'm just going to start from scratch here again. So we're going to say data sets using plots. Okay. Okay. One second, I need to pull up something. Okay. So let's go ahead and load the iris data set again. So this is how you access this module here. So iris, no, actually. Data sets, and then we want the iris data set. Okay. So anytime that you're curious about like documentation behind my code, you really should go and look and just say R, for example, data sets. Come here, and for example here, right? So I encourage you to look at the documentation behind any package that we use. So we're also using plots, right? So okay, and then become familiarized with the syntax and how to overlay plots and things like this. Okay. All right, so back over here. So we load this. And now iris is a data frame, in a sense, if you're familiar with data frames from Python. So like before, we're going to say, so x data is equal to, and we're going to use list comprehension here. So x for x in zip, iris dot sepal length, say,
Professor, can you zoom in and I cannot see it. Maximize and zoom in.
oh, so you want me to make the font bigger for you?
Yes.
Okay. Let me do this.
Or just maximize the window.
Is that better?
Thank you.
Okay. All right, so we're going to look at the first 100 entries in here. So I didn't ask this last time because I was moving kind of fast. Does anyone have any questions about what this code is doing right here? Anybody? So everyone's good?
You said zip just makes it into a tuple, right?
Right. So for example, yeah, let's take this time and this part of it. Let's finish this lecture off with like talking about syntax of Julia real fast. So suppose you have like A is equal to like 1, 2, 3, 4, 5 or something like that, right? And B is equal to say like, whoa, I don't know how I did that. Like A, B, C, and D, right? So I can just say for X in zip, A, B, print line X. And let's see what that does. Did you see what happened there with zip?
Mm-hmm. Yeah.
So if I had like another one too, like C is equal to 10, 11, 12, and 13, and 14, something like that. I can do the same thing with 3. Oh. So that's what it's doing. So X for X in zip, it's just taking, so if I look at like iris dot sepal 1 to 100, right? This is just an array. Oh, where is it? Nice. Oh, I haven't run this yet. No, this is still loading up here. Takes a second the first time you run it. So, all right, so this cell just ran. So here, it's just an array, a 100 element array. But so what does iris look like actually? Did we look at that much last time? So this is iris, right? So we have the measurements for sepal length, sepal width, petal length, petal width, and the species. And we can access the columns by saying dot that column. So like dot sepal length is this column here, dot sepal width is this column here, so forth and so on, right? So what this is doing here is it's saying the tuple X such that the first entry comes from this array and the second entry comes from this array. So you see 5.1, 3.5, 4.9, 3.0, 5.1, 3.5, 4.9, 3.0. So all I'm doing is extracting from this data set the first two features of the species. So the first two species of this is, first two features of this is a setosa. First two here, so forth and so on. But notice that you see all setosas, but if I look at Irish dot species 50 to 100, we see that those are all versicolor. And if I did 100 to 150, they're all virginical. So what we're doing here is we're looking at only the setosa and the versicolor, and we're only looking at the first two features of the data. Because the data altogether, right, has 4 features, okay? So that's all that this is doing, is looking at the first 2 features of each element. But now we also need the labels, right? So the Y data, or the label data, right, is I'm gonna say, so X for X in iris dot species 1 to 100. So the first 50 are going to be setosa, the second 50 will be versicolor. But notice that these aren't numerical values. We need these to be numerical values, so what we can say is, so like 1 if, so like 1, let's say, I don't want to be too fancy, but no, all of you should be able to figure out what I'm doing here. So we're going to say iris dot species I equal to setosa. If that's true, we're going to return 1. Otherwise, return a -1 for I equals 1 to 100. So does everyone understand this? And this right here is called a ternary operator. So any questions on that? So now we have 1s instead of -1s. Ones instead of setosa, negative ones instead of first light color. Does that make sense? Again, this is a big part of what we're going to be doing this semester. Like every time we encounter a new algorithm, we're going to have to take a data set and kind of parse it to get the data that we want. So picking the features is called feature extractment. So here we pick the first two features, right? So can I move on from this code? And I just want to make sure that everyone's on board because we're going to start programming a lot more in the coming weeks. We good?
Yep.
Okay, so now we need to plot this data to look at it. So the perceptron algorithm only works when the data can be separated by a line, as I mentioned last time, because what we're doing is we're generating a line to split the data. So whenever you want to test whether or not you can use a linear separator like the perceptron, you need to plot it to take a look at it. So I'm going to say scatter, because I'm looking at points, right? So we say scatter, and we're going to say X data. And we know the first 50 are going to be the setosa flower, right? So I'm only going to plot the first 50. Okay. And I'm going to give this a label setosa. Okay. And I'm going to say, since this is the first time we're plotting, I need to give axis labels. I'm going to say x-axis, in this case, is sepal length, right? So x-axis equals sepal length, and the y-axis is sepal width. Okay. And then I'm going to give the title of the plot a name. Iris data. Okay. So what that does is, so the first time you use the plots library, it takes a second to run. But what this is doing is it's going to scatter the points in the plane. Okay.
I think that you only wanted to fit
150, right? Right. So, but notice like we get all these points, right? What happens if I do this? Scatter X data 50 to 100. Oh yeah, 51 to 100. Okay, and this I'm going to give the label reverse side color.
Shouldn't the first scatter plot be 1 to 50, not 100?
Well, let's kind of play around with it real fast. So what if I do this?
Okay.
That looks different, right? So if I like comment this stuff out. So look at the scaling, down up to 4 over to 7. But if I do this, it doesn't go up to 4 anymore. So what happened is this original plot was destroyed by this one. So in Julia, whenever you want to alter something, whether it be an array or a plot, you put an exclamation mark. And that says that this is going to be overlaid with this. So now those blue dots over here were overlaid by this and they became red. But if you wanted to like not plot all the points like that, you could do this and you'll get the same plot. Okay. So now, like, we can see that this is linearly separable. So what many of you are going to need to do is to comment your code, and not many of you, I mean all of you. So, read the data set from our data set. Okay. Extract the first two features from the first 100 entries of data. Code labels with a numeric value. I'm going to like plot data to verify that it is linearly separable. So it's what it's trying to do here with this function is it's trying to give it a doc string. We don't need to worry about that. So, okay, so now the code has some type of, you can remember what you're doing when you look at it instead of having to figure it out. Other people, when they look at it, they see that you know what you're doing. Okay, so that looks good to me. Okay, so now let's go down here. And what we need to do now is, so we need our activation function, the sign function, right? So, oh, by the way, all of you will also need to do this. Where is below? Hold on. This thing needs to move out of my way. All right, so I see how there's a cell here. Well, now we can make this a markdown cell. This can be the Perceptron Algorithm. Right, so markdown syntax, markdown cheat sheet. I always forget markdown, so I pull this up a lot. So like you have your headers, bold, italic, and what you can do over time is you can make basically things that look like this. And that's the kind of the goal. You want yours to be as professional looking as possible. In this notebook, we implement the Perceptron algorithm on the iris sets. And then, for example, let's say like here. So it's just, all right, so that's how you would put a link in. So you can say, okay, and then go find the iris data set. Copy that link, go back over here. That way. There. Let's find me. All right, so shift enter, and then now you have like a hyperlink to go here. Okay. And then what I would like all of you to do is to go in and to give a description of exactly what's going on here. Okay. So for example, here I would insert a cell below, come right here, markdown. Okay, so you could say something like Perceptron Algorithm is the sign function to update the weights. Just you fill this in, basically. And you can use mine as a template, just don't copy mine verbatim. Write in your own words what you notice when you're doing your own notebooks. Okay, so I would definitely put in a thing underneath there. I'm not going to do that for you right now. I'm just going to say, okay, now we need to write a function for the sign function. So we're going to say function sign of weights and a vector x. So notice, so recall from last time that the weights and the vector x have different sizes. So just remember, just make sure that we nail this down. We don't have it all. So weight 1, weight 2, weight 3. So feature 1 goes there. Feature 2 goes there. And then the number 1, which is for the bias, goes there. Okay. And we take a linear combination of those, and then we apply the sign function. And that gives us a prediction, which is either -1 or 1. Okay. So notice that we have to change the size of x in order to make this dot product work. Right? X is equal to this, right, which is x1, x2. For the weights, there's 3 weights. Weight 1, weight 2, weight 3. Again, the weight is for the bias. So in order to make this work, we need to say, we need to change x to look like this. I'll call that x hat, right? So then what we're really doing here is we're looking at sine of w times x hat. So we've had to, our feature vector, we have to add a 1 to it to make it compatible with the dot product with w. Very important thing to note, because it doesn't, we're only looking at 2 features. So because w has to account for the bias, we need to add a 1 to x. So, let's see. Can we pull my screen back up? Where is my, there we go. Hold on. There it goes. Okay. Okay, so how do we do that? Well, so recall weights is a 3-dimensional vector, x is a 2-dimensional, we need to update it, so we could do, let me just try something with this. There. So in Julia, you can use math symbols, which I kind of like sometimes to match what's on my board. So you do x backslash hat and then press tab, you get a little x hat. And this is going to be the vector where the first entry comes from x, the second entry comes from x, and then we add a 1.0 there for the bias. Okay? So then we look at, we're going to say return W transpose times X hat greater than 0. If it is, return a 1. Otherwise, return a negative 1. And then end. Okay. Oh no, not W. What am I doing? Weights. Okay. So that'll be the sign function. Okay. So let's pull this over here. So everyone sees that should work, right? Again, that ternary operator might be new to all of you, but it really is just asking a question. If that question is true, like if this proposition here is true, then it returns this. Otherwise, it returns the negative 1. Okay. All right. So when writing functions in Julia, if you want to be as professional as you can be, documenting functions in Julia. Wrong link. Documentation here. So here's a function, and this is how you would document that function. And it gives an example, and you can read through here and see exactly how you should document these functions that you write. For example, you documenting this one. Okay. So again, the more detail that you put into each notebook, the higher chance you are of getting a 10 out of 10 for that particular notebook. Okay. Okay. So next we need to write a function for the update rule. Okay. So function Perceptron. By the way, at any, like, y'all being surprisingly quiet. I don't know how many of you have experience programming in Julia, but please just stop me if you feel like there's something that you don't understand. Okay. So what do we want to do? I'm going to say that if the sign of weights and x does not equal y, which is the correct label, we want to say weights equals y times our vector x. But remember, the dimensions of weights and x have to match up. So x1, x2, and then we're going to put a 1.0 to make sure that those dimensions match up. And this is plus equals that. Okay. And that return, and then end your function out. You always have to end your functions in Julia. Okay, so what we're going to want to do is consider how many times we're getting the answer wrong. Right, so we're going to write a very simple error function error. So if we're given weights, right, and then we're going to have, and this is over the entire data set. So I'm going to say feature set labels like that. So return sum, okay, of say G, what am I doing? Sine of weights times X not equal to, trying to figure out the best way to give my variables the right name. Feature set I. The sign of that not equal to labels I. So how many times are you getting it wrong, basically? That's what this is saying. Like, if your output does not equal the correct label, you want to sum that. Right? So, oh, I need to put this in an array. Sum only works over an array. So sum of that for I equals 1 to 100. So if it doesn't equal, we're going to give it a 1. Otherwise, we're going to give it a 0. And we know that we're going to have 100 things in there, so this should work. Okay, and again, like each one of these functions, if you want the highest possible grade, should be documented well. So do you guys understand what's happening here? We have the sum of what? Well, we have an array. Well, what's in that array? So we're going to check the sign not equal to the correct label. If it's not equal, we put a 1 in there. And if it is, we don't count it, it's a 0. Okay? So basically, we're summing up how many times we get the wrong answer. Okay? And actually, if you wanted to be more specific and be able to adapt this for a different data set, you can just do something like length of your feature set. Okay, so for one, so you're just going through all the data. Okay, so hopefully there's no errors there. Okay, so now let's implement the actual algorithm. So, and notice that I'm breaking up this problem into like a bunch of functions. So we have weights. Oh no, we don't need that. Yeah, so weights, and then we have our feature set, and then our labels. Okay. And then I'm going to put in an epsilon for the error. So backslash BP epsilon, and then press tab. Okay. All right. So while error of weights feature set labels is greater than some stopping point, epsilon, we want to do the perceptron update. So weights equal perceptron updates for weights. Well, I need to go through the whole. So perceptron update works on just one entry. So while the error is greater than that, we can put a for loop in. So for I equals 1 to the length of the feature set, weights equal perceptron update weights feature set I labels I. Okay, so that just updates our weights. And notice we go through the entire feature set each time we get a bad error. Okay, end. So what I'm going to want to do, just to visualize things, I'm going to say that error measures equals to this. Okay, and then error measures dot, no, I forget I'm not in Python. 1 second. Julia and to array, just so I can remind myself. Yeah. So it's with an exclamation mark because you're changing the array. So we start with this empty one, append, error measures, error weights, feature sets, labels. So what that does is it puts into here the first error that you calculate. Okay, and then weights. So I also want to save all my weights so I can show you the changes in the weights. So weight vector equals weights, something like that. So we can save the weights for each of those. So after we update our weights, I'm going to say append weights vector, comma, the new weights. So we alter the weights, and then I'm putting them in here because I want to save them to look at them later. And then I also want to append my new error. So append error measures error weights sets labels. It's kind of concerning. Oh, this should go outside. There. No, I was right the first time. There. So that ends that. That's concerning that it's tabbing over because it shouldn't be doing that. So return weights vector error measures. Something is bothering me right here. Something, I bet you there's going to be an error somewhere. Yep, where is that missing? Does anyone see it?
I think it's with the first append.
Yeah, you're right. Right there. Okay, so let's see if this works. I'm going to say W, capital W, errors equal to Perceptron Learning Algorithm. I'm just going to do a rand with a normal distribution 3 vector, x data, y. That's what I labeled the things, right? Yeah. X data, y data. All right, let's hopefully not get an error. Oh, I almost forgot the epsilon. So while this is, let's say while the error is greater than 2 or something for my epsilon right here. Oh. Got an error. Cannot convert an object type float, so somewhere in here. So what's happening right now, so types are important in Julia. And most of you have been working in R and Python where type conversion happens naturally. So what this is telling me here is that one of these arrays here, either this one or this one, has an initial type and then it's becoming changed over time. So what I'm going to do is I'm going to make this empty so it doesn't know the type initially. Let's see if I get the same error. All right. Looks okay. So let's go ahead and plot the errors. So you can say plot errors. And let's just take a look at what this looks like. So label number of misclassifications. That's what it is. It's the number of times you get the wrong answer. Do we really do it in 50 times? So notice the first like 20 iterations. So this is, so what does errors look like? Errors is this thing right here, right? So when you plot when you use the plot function on points, it connects them. So maybe I can just do this to show you. So I'm going to overlay on this the scatter of errors. So when you use plot on points, it just connects them. So notice like we're doing good. We did better, doing good, get better, better. And eventually the number of errors or misclassifications is below the threshold that we chose, which was 2. You see that? So that's good, and it did it pretty fast though, right? So now let's think about what happened. So if we look back up to right here, so what are we doing when we look at this linear product right here? So I'm gonna pull my screen back up. So we're looking at the sign of W transpose X hat, right? So if you look at that product of that times that, what do you get? You get X1 times W1 plus X2 times W2 plus 1 times W3. Okay? That's what you're getting, and you're looking at the sign of this. But what this is really defining is something like, this is defining a hyperplane in 3-dimensional space, right? You like think back to your second calculus course where you did three-dimensional plots, right? You have an x1 and an x2, and you have some multiples of them, and you have your plus b in a sense. That's going to define a plane in three-dimensional space on the z-axis, right? It's like x, y, z, right? Now a plane in three-dimensional space is going to cut through the xy axis when z is equal to 0, or the third variable is equal to 0. So if you set this equal to 0, you get the line in the two-dimensional plane. Now, if you want to know what this line looks like, you just solve for x2. If you solve for x2, then you're going to get the line that you're curious about, right? It's passing through the two-dimensional xy plane. So if you solve for that, what do you get? You get x2 is equal to negative x1 w1, move that over, minus w3 all over w2. So this is the equation of a line in the xy plane that we've learned, and that line should be a separator for the data. So negative x1 w1 minus w3 over w2. Okay, so if we go back to here, okay, so, all right, so if we want to look at that, let's just go up here, copy this again, copy, paste. Okay, so let's look at plots, and we're going to say x goes to, so a quick way of writing lambda functions, negative x times w1 minus w3 divided by w2. And we've defined w up here, right there. That's the weight vector that we learned. Okay, so, oh, and I need to put the exclamation mark to overlay on this data here. And there's the separator. Okay? So now, I guess it's not perfect, right? We have this one misclassification, but if we look up here, we set the error to be that. So while this is greater than 0, we want to run it. So let's do it again. There it goes. It did take longer this time. It took a lot longer, 700 times. But now, copy that, paste it here. So this is going to change the plot again with the new W that we have. Yep. Oh, I was overlaying this plot. That sucks. I should have kept this one. But there. So this is after we ran it 700 times, we get this separator. Okay. So if you were wondering how to make that line, the idea is that this is the intersection of a hyperplane that I drew, like that equation that I drew on the board. A hyperplane is just a flat plane in three-dimensional space. And it's intersecting two-dimensional space precisely when the z value is 0. So by setting z equal to 0 and solving for x2, you get a line that cuts through space. and it's the separator that you want. So now that you've learned this line, if you land on this side, you're setosa. If you're on this side, you're versicolor. Okay? Now, what I want all of you to do this weekend is to change the data set and look at different features, right? So, like iris, recall looks like this. We looked at the first two. But what about if you look at sepal length versus petal length, right? So if I come up here, what was it down here? Yeah, petal length. So I come back up here and I change this to petal length. And I plot it. Notice the data looks different, right? Because now, oh no, this is I'd have to change this to so I would like it if maybe you can this would be an assignment for you for one of your notebooks, one of your directories in your GitHub account, is to look at all the combinations that you can of two measures of the setosa and the versicolor. You get all the different combinations, plot them, and determine which one you think best, which combination of features you think is best suited for performance using the Perceptron algorithm. So you'll have what a small number of things to do, like sepal length versus sepal width, sepal length versus petal length, sepal length versus, and so forth and so on. Exhaust those combinations and try to determine which ones are easiest, right? So for example, remember this one took 700 times when we had it the first time around. Let's see how many times it takes this time. So, oh, it did it in 6 goes. And it found the line that perfectly separated it when it was, you see what I mean? Like this took much less time. It took 6 iterations before it classified everything perfectly. Whereas the original one took 700 times. So your job for one of your notebooks would be to implement this algorithm on the iris data set and determine which features are best suited for the Perceptron algorithm. Okay, and then once you get a template of this notebook going, I would like it for all of you to send me your GitHub accounts so I can look at it and give suggestions on how to make it a better looking notebook. Okay, so that will be it for today. Please get started on that notebook so I can be assured that everyone has made a GitHub account and is starting to get started on the programming aspects of things. Right? Everyone stay safe, and I will. I'm making a YouTube channel for this course, and I'll post a link to that YouTube channel later today.
Dr. Davila, do you post the notebook to the Blackboard or in your GitHub account?
There's one that's similar on my GitHub account, but I'm not going to post what I did today on Blackboard because I want you to kind of fiddle around with it on your own and just start from scratch and type it all up on your own.
Okay.
All right, so that'll be it. Everyone stay safe, have a good day, and email me if you have any questions about how your notebook is looking. I look forward to discussing these next Monday.
Sounds good. Thank you, sir.
Professor,
Yes.
where I can find the link to the YouTube?
I will post it on Blackboard later today. It's not up yet.
Where's the first project?
Say that again?
Will you post the first project?
Yeah, I'll write something up and more descriptive than what I said in the video if you need to, if you need me to. But basically, it's the same. It's not so hard. Just write a Jupyter notebook that goes through the different combinations of features from the
Okay.
and then determine which one you think is best for performance on the Perceptron.
Okay. Thank you.
All right, talk to y'all later.
Can I add one more question? So
Yeah.
for the project, like you want us to do the assignment, like find the best feature for this data set, or like we create a new data set and doing the new for the project in the Perceptron?
You can use the Perceptron on another data set. I just thought that it would be a good template, a good exercise, a good idea for you. Like I can give you suggestions. You don't have to do it, but I think that to get the semester started, I think everyone should try this one just so I can give everyone personal feedback on how they're laying out their notebooks.
Okay, so we do this for like practice, and then we have another one for the project.
You can use this one for the project. You can,
Okay.
if you want to. You don't have to, but you can use this one for the project.
Okay. Thank you.
All right. I talk to you later.
About my Julia, when I run, when I do run sign and I run error, it gives me a base function error. So I usually have to capitalize them. And when you do them, it doesn't pop up. So I was gonna ask anything about that.
Can you send me a screenshot of exactly what's going, or just send me your notebook and I can open it up and look at it.
Okay, I'll send it to you.
That sounds good.